You're listening to Let's Talk AI.
Okay, good day. This is our next episode of Let's Talk AI. Today we have Gautam Kamath from our Cheriton School of Computer Science. And Gautam's going to talk to us about his journey on AI. So welcome, Gautam.
Thanks, Harold. Yeah, it's great to be here.
So tell me a little bit about, let's just start off with your area of research and work, and tell us more about that, please.
Yeah, what gets me really excited and up in the morning is trying to understand statistics, machine learning, AI, and all these things, but through the lens and with the constraints that nowadays come up in modern data analysis. For example, like we built this toolbox of tools, statistics is quite old, and machine learning over the last, 20 years has been a lot of amazing work done. But some of the considerations that come up in modern data analysis settings weren't really considered when these sorts of things were first dreamed of. For example, things like robustness and privacy of the data. These are things which are kind of new and not super well explored. There's been a lot of interest recently, but I think there's a lot of catching up to do, and I'm hoping to help our understanding of these areas get caught up.
Okay, so where did this all start for you?
It starts like how did I get into AI, machine
How
learning?
did AI, machine learning, and where was that epiphany, that light went off and said, "Wow, this is a field I want to study."
Yeah, it's I guess everyone, it seems like all of my friends are converging to machine learning type problems in different directions. I personally started from a more theory point of view, in the sense when I was an undergrad, I really liked math. I really liked, computer science. I liked algorithm design, analysis of algorithms, stuff like that. And I just thought, okay, I want to do this more. And so I went to grad school with kind of no real super well-defined idea of what I want to study. I knew I liked math. I knew I liked probability. Probability was really cool to me. Probabilistic style of thinking and stuff like that. And yeah, it just kind of happened that I talked with my advisor. He had some interesting questions in statistical questions. And the way I'm sure many people have had the same experience in kind of doing research and doing in grad school, you ask one question, maybe solve that one question, but then two new questions come out, and then two new questions come out. And I felt like some of the questions that really seemed most interesting and coming out of it were maybe theoretical questions in statistics and machine learning. So it just kind of naturally flowed down this path, and I found myself asking, theoretical questions about statistics and machine learning first of all. But then that's not the whole story. I guess at some point, I think I realized that a lot of this work that we do in theory is also relevant, and it kind of is targeted. We're trying to fulfill a promise in some sense that these things will hopefully be useful to like real problems. So nowadays, I sit kind of somewhere between theory as well as practice in terms of understanding how to do statistics in ML.
Okay, so you clicked on a term or touched on a term earlier called robustness. How would you define that in your term, and what is it? What is non-robustness? Put it in those references.
Yeah. Good question. I'd say that people, when we're analyzing and designing algorithms for things, we usually like to imagine things are very, very nicely behaved. For example, there's a classical joke, I guess, where physicists say they imagine everything to be spherical. Like, this problem is okay as long as you have spherical cows or something. Similarly, in statistics and in classical statistics, the stuff dreamt of over, say, like 100 years ago, that type of stuff really assumed that we had some sort of perfect models. Our data is generated from some sort of nice distribution, or things are well behaved. But nowadays in data analysis, it's rarely the case that things fit our perfect settings, which may just be, simplifications. Yeah, nowadays there might be all sorts of reasons. We might have much more complicated data distributions. Data comes from more complex sources, or even of a lot of attention nowadays is trying to understand what if there's an adversary in the system, someone, a malicious actor who's trying to change your data set in order for their own selfish gains. So obviously, over 100 years ago, this wasn't really the forefront of their minds, but given the state of how data is generated and collected nowadays, that might be of more importance.
Okay, so if there was, such an adversary and it got infiltrated into a set of data, how would it be identified? And does the model have to back up and redo its learning before it recognized that adversary was there, or how does it solve it? How does it get rid of the adversary?
I think it's really hard to tell in a lot of cases. Like, let me give you a very popular question in this area, which in the general area of robustness. One popular question, which we still, despite its simplicity, we don't have a very good understanding of how to handle it. And this is something called adversarial examples. So to sort of give some context, imagine you have some sort of machine learning model, which is supposed to tell you if, say, a picture is a picture of a cat or if it's a picture of a dog. Now, we are very, very good at this task. We can build neural networks, which can get like 99, almost 100% accuracy on this type of task. But the issue is the following. If an adversary takes one of these pictures in a test set, like it feeds a picture to a neural network or a machine learning model, which looks like a cat or a dog, but it turns out that they can make imperceptible changes to this picture, and then pretty reliably they can make the machine learning model think it's a dog instead of a cat or a cat instead of a dog. Basically, flip the model's prediction on it. And this is kind of like one of the attack model that you might look at. And the kind of troubling thing is we don't actually know how to perfectly solve this type of problem, in the sense that there are some defenses. For example, one defense is similar to what you said, where maybe you have to take a step back and try to maybe take into account the fact that the adversary exists. For example, basically you can retrain your model, but retrain your model knowing that that there's an adversary who's trying to do this, and take that into account when you're doing the training procedure. But nonetheless, it still seems like for more complicated settings, we don't know how to handle these sorts of things, and this is a major open problem in machine learning nowadays.
Okay, so if I'm from industry and I put on my hat, I don't robustness probably doesn't resonate with me, but this term trustworthy machine learning does. How does robustness, trustworthy, are they synonymous terms, or what's the difference?
I think, yeah, trustworthy machine learning encompasses a lot of different things. I'd say trustworthy machine learning, like let's just state the obvious. And what does it mean? It means that an algorithm should be trustworthy. It should be that when you deploy this algorithm, it behaves kind of as people expect it to. Now, this is often not rigorously defined in the sense like we don't have guarantees of everything that will or won't happen when you're running a machine learning model, but it should kind of behave as we would like it to. For example, you should be able to trust that this instance I gave in terms of robustness, that's one form of trustworthiness, which is that, if you have something which a human would say is a cat or a dog, then maybe the machine learning model should think it's a cat or a dog as well. That's one aspect of it. Another aspect which I've also done a lot of work on is understanding the privacy aspects. For example, would you trust a machine learning model when you give your data to a machine learning model to be trained? You typically trust that it's not going to reveal sensitive information about you. That's something that you'd also want a trustworthy model to be able to respect. Just things like that, I'd say. It's sort of a more broad term, but I'd say trustworthy machine learning is kind of synonymous with the sort of modern considerations in data analysis that I kind of referred to earlier.
But is it the same level of comfort we have with, most people's computers are constantly attacked by viruses? Probably not so much these days with our great, virus prevention tools and things like that, but there's still occasionally one that gets through. Is it that same level of just awareness, but it's not something that's going to hold us back moving forward in AI?
I think, yeah, you hit on a sort of good point in the sense that in terms of some of our uh, more mature systems, things like operating systems and stuff like that, I'd say we have pretty good understandings and pretty good things are relatively safe in a sense. I use air quotes around safe because we understand how these things work. We kind of understand where they'll go wrong. We understand the sort of expected behavior. Whereas for a machine learning model, I'd say it's much, much less on all of these fronts in the sense that things could go wrong in a bunch of ways. We understand, some of which we understand okay, and some of which we don't understand well at all. Yeah, I'd say it's kind of much more like the Wild West right now in terms of what we rigorously know and control and can control. There's a lot more work that still needs to be done in comparison to more classical systems. Just for one comparison, like imagine a space shuttle or a car. These are very high reliability type settings where you can't have something going wrong with a space shuttle because if it blows up, there goes your multi-billion-dollar investment maybe, or hundreds of $1 million investment. Machine learning models are nowhere even close to something as trustworthy as something like a space shuttle.
Okay, well, that's a good comparison. So I'm going to focus now the spotlight on yourself. How long ago did you join Waterloo? And I see that you're part of the salon. What is that all about?
Yeah. I joined Waterloo in July 2019. So I think I've been at Waterloo maybe like 4 times longer now remotely than in person. So I've been a very remote faculty, given when the pandemic started. And yeah, when I just when I was joining Waterloo, I decided to come up with a name for my group, my students, because yeah, I don't know. I just want to have some sort of feel of community, which is, I think, very important to me. So I called my group the Salon, which stands for Statistics, Algorithms, Learning, and Optimization. I cheated a little bit with the last one. The N is the N at the end of optimization. But yeah, I chose that as the name. It kind of refers to the practice kind of from, I think, Renaissance era in France, where people would get together and discuss some of the biggest ideas of the time, philosophy amongst other things. And I just like that idea because that's what I want my group to be like, bringing together bright people to discuss interesting ideas. I explicitly avoided, some people just choose their last name, Kamath Lab. I didn't really like that because I wanted to make it clear that this is about everyone, not just me.
Okay, and well, just for me as the non-mathy, when I hear n, I think to the nth degree. So maybe all of the SALO to the nth degree, it perfectly goes. Um, Great. So an area that I see occurring across so many fields, so many areas, and especially industry asking about it is how much data do I need to be able to put through my algorithm? So maybe if you could give us a little bit of your insights about that. How much data? What is big data? What is, the quantifiers around that?
Yeah, it's a very good question. I think, yeah, a lot of people throw around big data nowadays, and the question is, what does it mean? What does it entail? I can give you a few perspectives on where I think uh, size is kind of important in machine learning, especially for data. I would say that one of the biggest successes in modern machine learning has been through things like, when I say modern machine learning, there's a lot of things in modern machine learning, but this is kind of one of the most recent trends since maybe around 2017. Uh, it seems like, especially for natural language processing tasks, that is, tasks which operate on text-based data, we've seen unprecedented improvements in accuracy using what are known, perhaps, they're called large language models by many people, which essentially these are rather large architectures, which yeah, very very large architectures in the sense that they're very big on big, I guess, to store and run. But on the topic of data, they're pre-trained on the machine learning model is trained on a lot of data, which is scraped from the internet. Imagine, downloading a lot of Wikipedia and downloading a lot of news articles and stuff. And you feed all of this, you just scrape a bunch of it and feed it all into an algorithm, into a machine learning training algorithm. And then you come out with a very big and powerful model. It seems like this type of pre-trained model, which just uses immense amounts of data online. It doesn't even have to be, uniformly good quality data. This seems to have been incredibly powerful in reaching new levels of performance on many of these tasks. So I think in certain aspects, in this aspect, I think this is, in this area, this is one clear success in my mind of where big data has been helping.
Okay, so let me just jump in for a minute.
Yep.
You've used the word big, you've used the word immense, you've used the word large. These are all very subjective. Is there a number? Is there 250,000 records, 2 million records, 10 million? Is there some benchmark as a researcher that says, hey, I don't have enough? Or is it not about quantity? Is it quality? What's that threshold?
I think it's hard to say in general, in the sense that for every specific problem you look at, every specific instance, it might differ very, very significantly. For example, there's two of the canonical, like, these are kind of baby tasks in machine learning. One is working on a data set known as MNIST. Let's start with MNIST. Is just a sequence of digits. Like, imagine someone hand wrote the numbers 0 through 9. And the other one is CFAR10, which has a bunch of pictures of just 10 different things. For example, dogs, cats, boats, etc. And these are two data sets which are roughly the same size. They're roughly the same size, and they both have the same number of different classes. They're kind of comparable data sets in some ways, but it's well established that the former task, MNIST, recognizing whether a digit is 0 through 9, is a much, much easier task for machine learning model than CFAR 10. So it seems like it's just not the amount of the data that matters, because it's about the same amount of data in both data sets, but it also matters how hard your task is. You could be trying to do something much more complex, and that would require a lot more data.
Okay. So we looked back, we looked now, what's ahead? Paint us a little bit of your vision of where do you see things going? Adoption, is it still at the university, academia, behind closed doors, the rollout? What's your vision? What's your thoughts?
I think simultaneously we need to, I think, there's a lot of hype right now, and I feel like we probably need to slow down a little bit and sort of rethink, though I'm sure there's other sort of industries where maybe it needs to speed up. But I think, like, there's a lot of hype and people just think it's a panacea, machine learning or AI can solve all your problems. I think it's very, very powerful, but I think folks need to slow down a bit and think about a little bit more than just this is going to solve all our problems, in the sense that I think people are sometimes using machine learning models in places where it's not appropriate, and maybe a human would be better suited for making this decision themselves. For example, there was a recent, maybe about a year or two ago, a feature on Twitter where if you upload an image, it would choose how to basically crop the image, or how to, like, display the image if you're on a device where it can't show the whole image because it's too big. And people noticed that if you put a picture with two individuals, say there was a famous one going around, one with former President Barack Obama and Mitch McConnell, that it would more often choose to focus the image, to shrink it, to show Mitch McConnell rather than Barack Obama. So the speculation was that it maybe whatever algorithm they used there preferred the light face instead of the dark face. That's a potential bias that could have been in the algorithm. It's not really, they claim they tested for this sort of thing, and there's been some audits done afterwards. And people have been thinking a lot about this. My personal opinion is this doesn't really even seem like the type of thing that a machine learning model was needed for. You could just ask the human to do this themselves. So I think, in my opinion, sometimes we see overuse of machine learning for problems. Another thing is that I think, again, people are willing to deploy these things, but without real concern of whether it's trustworthy in the sense that we kind of described before. For example, self-driving cars is one of the big hype things, but one type of issue is whether these are trustworthy and can handle edge cases. It seems like right now you hear now and then about accidents and weird cases, but there's also very simple cases where you run into issues. For example, I remember seeing a picture where or a video maybe of a Tesla driving, and it was trying to use full self-driving, but it was recognizing the moon, which was big and yellow looking, as a yellow light. I think something like that. Or maybe another thing maybe with a billboard or which had a picture of a stop sign on it, and the car was interpreting it as a stop sign. Now, these might be okay if you're doing it in a low stakes environment. If you're using machine learning in a low stakes environment, that's fine. But for something like a self-driving car, I think you would need much more trustworthy and reliable machine learning for that sort of thing. And a final thing is, I think a topic on a lot of people's minds right now is data privacy and trying to understand, when you give your data to something, to some organization, what does that really mean? What are you giving up for it? And I think nowadays a lot of people realize that the data that they're revealing about themselves can be rather revelatory. It's giving a lot of ammunition to understand things and build profiles about people, and maybe things that people are not really comfortable giving up. So I think there needs to be more understanding as well about what are the privacy guarantees and what are you kind of agreeing to when your data is given for being used in a machine learning setting.
Well, it's funny, if you think about the EULA, the legal disclaimer at the every time you log in, you'd almost need to be a lawyer to understand what exactly it is you're giving up, and so that definitely looks like an area that we're going to need some more insights, or maybe we need a short form EULA of they just say we will not use your data, period, and not put it in some of the more complex terms the way it shows today. Well, we've got some great insights from you today. Any final closing remarks, things you want to talk about related to data or this concept of what's a data scientist versus, different things like that? Any other final closing remarks?
I guess I'll just pick up on the last thing you said, which was, it's a very difficult thing. Privacy is a difficult thing for a lot of people, but I think that's why nowadays experts and policymakers are kind of trying to fill this void by realizing that there's a big difference between what people want in terms of privacy and what they understand and what they can handle. The average person doesn't have the time or attention to read through absolutely every little detail about how their data might be used. So I think it's interesting to see how various different countries and organizations are coming up with new privacy legislation. For example, one of the most high-profile ones of this is GDPR, of course, in Europe, where I'm sure a few years ago all of you got emails from everything saying that they're updating their privacy policies. And that's because Europe essentially said that we're taking privacy very seriously. And if you don't obey these types of restrictions, then you will get fined significantly. And so it's heartening to see, for example, in Canada, we have some proposed legislation, which I think is currently being considered. I haven't looked at it in a while, but maybe the last six months to a year. So I think things will get better, hopefully, though the sort of this is perhaps one might think that this is far from what machine learning folks care about, but I think this impresses the idea that there really needs to be communication between technical folks as well as policymakers to try to understand and come up with the right type of restrictions and policies that we have in the future.
Excellent. Well, I appreciate your time today, and thanks for participating in our Let's Talk AI.
Yeah, thanks a lot, Harold. It's been great to be here.
Awesome. Well, you have a great day. Take care.